I'm actually trying to, well, we're trying in collaboration to actually take this vision and try and do the first steps. This is what we call our drone-to-drone communication project. I'm very happy to be here. I'm very much looking forward to going over there and testing it. As we've seen today, I, for one, as a computer geek, are very much excited about this. So just a bit of a heads up before we start. I am a computer scientist, so this is going to be a bit geeky. Fortunately, for those of you who doesn't really care about frameworks and so forth, it's only going to be a couple of slides. So you can fade out and then you can come back. Just a quick warning. So first up, let me just quickly introduce the Alexandria Institute. We are a private research organization, GTS Institute as it's called. Our mission in life is basically to take the newest research from universities and put them into play with the Danish companies. We are the GTS Institute that's focused on software as opposed to some other GTSs. So now you know, let's move on. So our project is actually called the Secure Drone-to-Drone Communication Project. It's a collaboration between Rambil, you probably all know those, a small startup called Miley Robots, and of course DTU Space and the Alexandria Institute. It's funded by the InnoSec Innovation Network. They've been so kind to give us some money to actually do this development here. So I'll start off by doing a bit of a description here of what we're trying to do. You saw the model over here on the right from Michael. I'm going to reuse it as well because I think it sums up fairly well what we want to do. So as Michael said, we don't really care about the modality here. So if they're driving, flying, diving, walking, it does not matter to us. This is actually just a protocol for communicating between these units. And it's not, I put it up here, it's not a catch-all, and the reason why I put it in here is just to be a bit humble. I don't believe that what we do here will be the end of time. It cannot solve every problem there is, but we believe it's a step in the right direction for we can actually start to utilize these autonomous infrastructures. I've also put, I've kind of read a lot of sci-fi lately, and you can probably see it here, encrypted swarm communication for the collective hive mind. I think maybe that was, I don't know if that's a Neil Stephenson quote or whatever, but it's basically what we're talking about here is multi-agent systems that can communicate and they can do it in an encrypted way. And as I put next, and I did this presentation a couple of weeks ago, and I got kind of apparently it's a bit controversial to say that it's hardened from the software pirate world. But what I mean is we're using the peer-to-peer principles here, and for most people when you hear the word peer-to-peer you think about Napster, BitTorrent and whatever, and so of course you think about pirating software. That's not a good thing. I'm a software developer. I do not like pirating software, but there is one good point here, and it's been hardened from being in that world for so long. There have been state actors for many years trying to shut down these peer-to-peer networks, and they haven't succeeded. So why not take a cue from these guys and actually try to use the protocol for something that's a bit more, let's say, productive. And also, I Googled it the other day, and it was actually also used in the Catalan independence referendum where the Spanish government tried to shut down access to information. And the independence community down there used peer-to-peer to circumvent the censorship. And that also plays into the fact that it's actually used as a Wikipedia mirror for enhancing access to information that state actors don't want you to have. So, it kind of sums it up fairly well, right? It is a resilient protocol that can be used to circumvent censorship and circumvent breakdowns. If we look at our more specific what we want to do here, I have a slide here called organization. So why do we want to use peer-to-peer, and why is this exciting in the context of autonomous systems? Because we don't like pirating software, that's not exciting in itself. And I think there's a couple of reasons for that, and I believe one of them is enhancing the resilience. If we actually have a breakdown today, at least for most people's part, if you have a breakdown in either an agent or in your control stack, you lose control. And for most of the time, the autonomous systems are programmed to just do a dead stop because this is a potential dangerous situation. And in a sense, I agree with this. But what we're trying to do here by utilizing this protocol is to have the swarm being able to organize itself. And don't really care if you have a breakdown, you can still fulfill your mission. So one thing is if the C2 or if fleet management system breaks down, but the other thing is if you have an agent that breaks down and the system will actually do this reorganization bit. I tried to draw it up here. As you can see, this is not my strong point, but I think you get the point here, right? That number 2 breaks down and then 1, 3, and 4 reorganizes. I do apologize for the lack of artistic quality here, but I hope you can live with it. The other thing is that we try to utilize excuse me, the features of all the agents, so of the different agents. So again, we don't look at the hardware or the platforms in themselves, what they can do. That's something the system organizes. We actually basically put out a mission that says do a sweep of this field here, and the system chooses the agents that can actually participate in this mission. So it could be flying, driving, or whatever again. And also, if an agent has some special hardware, we might want to take that into account as well. So we've heard a lot about machine learning algorithms, deep neural networks, and so forth today, and that's all very good. But I think everybody, or most people in here at least knows that these algorithms are very much energy thirsty, to put it mildly, right? So you probably don't want to have too much machine learning running out on a battery-driven agent, because at some point it runs out of battery. So maybe we want to utilize the fact that you can have a basic IoT unit on what do you want to call it? Fixed power lines that doesn't have the battery contingency, so we can actually utilize that. So basically have the machine learning algorithm running on a unit that's connected to a power line. Again, you can just move the data around, but the swarm takes care of it itself. Damn. And the last part I want to put in there is it minimizes the network latency. This is meant to run on its own, not on its own network, but it's meant to run on the same subnet. So instead of us trying to send the data up to a cloud platform somewhere, we don't know where, it could be in Frankfurt, it could be in New York, we actually try to utilize the fact that we can put the agents inside the network, so we minimize the latency going back and forth. Again, it's also about resilience. If the internet breaks down, it does happen. We can't connect to our cloud provider. We're kind of screwed. But in here, we have control of it. We know where it is, and we know it's in the swarm, so we can always access it, and we can access it fast. The other part is I want to talk about is the context. So this is actually taken from a slide I used earlier for the Homeland Security Conference, where they wanted to know, so what can we use drones for in a security context? And as Michael said, all the agents know about each other in the swarm. So again, you can actually use the inverse, that if they detect a unit that's not part of their swarm, then it must be, well, maybe it's an intruder, but at least it's somebody not supposed to be there. So if you have these agents flying around, let's say a harbor, and they suddenly spot a drone up there in the air together with them that they don't recognize, they can like point up a flag and say, hey, there's something wrong here. You could probably program them to just ram into the drone or whatever, but that's not the purview for this algorithm here. And you can actually use any types of data source of sensor in this network. I've listed a couple here, RGB, thermal, radio, whatever. And it doesn't really matter, we're quite data agnostic. We try to move the data around inside the swarm by just breaking it down into byte arrays, so it's easily to utilize in different settings. So, if you want to do some image recognition, you can do that. If you want to do some detection of particles in the air, you could do that as well. We just facilitate the movement of the data around. So this is probably the slides where some of you may be able to fade a bit out. Now you're warned. I'm just going to talk a bit about the technology, because I think it's actually quite fascinating what we're doing here. I've tried to list some of the technologies we use here. This is just the basics. We use Golang, the programming language. It's very efficient when it comes to concurrency. We use libpeer-to-peer, which is an open source framework for doing this communication. We're building on top of that. Again, we don't try to develop everything from the bottom up. We actually try to utilize what is already there and what is actually available to us from the components outside. And libpeer-to-peer is actually open source. It's developed by the IPFS community, and that stands for Interplanetary File System. I still don't understand the naming, but it sounds pretty cool. These are some of the guys who were participant in actually developing some of the early peer-to-peer protocols I mentioned earlier. So they do have a bit of knowledge of what they're doing. It's actually, I thought when I started looking into this, I thought, okay, so this is only some geeks in the dark corner of the internet trying to figure out how can we pirate software without being caught. But it actually dawned on me when I drove into it that it's actually being used by some quite big names. Microsoft Cloudflare and the Brave browser is actually using this technology for some of their works. And I think that's pretty interesting. It just shows that this technology is not just for a subset of people, it has potential. And historical context, the internet was basically a peer-to-peer network to begin with. We just added this server-client terminology on top of it because, I don't know, it's probably easier. Then we use ROS, I guess most people in here know that, and we utilize Three.js, which is a visualization tool, and Unity, the game engine as well. I'm just going to go for a quick talk down technology lane here. Let's start at the bottom. So Unity, most people know this as a game engine. I think Assassin's Creed is probably built on top of it, and some more games I can't remember. But we use this for visualization and simulation. Rambøll, one of our partners in the project, is building complete 3D model of Copenhagen in Unity, and we're going to use that for doing simulation and seeing how it actually works in a simulated setting. And of course some visualization as well, because Unity does look pretty cool when you look at it. Three.js, which is a more low-level visualization tool for browsers, we're going to use for actually looking into the protocol, try to debug. Basically, it is kind of hard to see what's going on when it's just sent data between the agents around the net. So, we want to have some visualization so we can show what's actually going on. And then lib peer-to-peer framework. I just mentioned some of the good stuff I like about it. It's TCP based, so basically when we're on a network, we don't care about the hardware stack, we only care about the software level. So as long as it's TCP connection is possible, we're all good. We use private public keys for security and authentication. We use a pub/sub mentality terminology, which is similar to what you see in ROS. Basically, you publish to a topic and people subscribe to it as well. And we utilize their gossip protocol, which they have developed, which is shown to mitigate the data through the network, not directly from one to another, but actually through hops, through the peers. And they have a guarantee that data is being sent to where it's supposed to go. So just let me end up with a bit of example here. We call it Where's Waldo? Most of us probably know him as Holger, at least us Danish-speaking people. But we want an example of what we use here and what we're going to hopefully show off in a month's time is how do we find Waldo? So in an urban environment, we want to use some different modalities. We want to use flying for the overview. We probably want to use some driving units as well, just to get under it. If it's down a tunnel, if it's under a bridge, somewhere where drones are not that easily going to go. And we're going to use some human detection machine learning inside the swarm as well, because we want to detect Waldo out there. We want to have some cameras out there, some sensors. And that's, we actually we utilize the basic REST endpoint for modality. So it's not completely inside the swarm. You can easily swap this out with different algorithms you want. So the example we kind of imagine in the flow is that we have one agent up there, agent B, who's going to break down. The swarm communicates and they agree, so agent B is gone. We need to reorganize. They recognize one of the agents as the one who has to do the reorganization. It could be basically all of the drones or agents in the system based on some parameters that we set. And after that's done, he sent as the chosen one sends out the mission to all the other agents in the swarm, and they agree on continuing their mission. So if agent B has already covered an area of, let's say, a building or a city, the other agents are not going to do a sweep of that area again. It's going to be tagged as being already looked at. So we try to utilize and just the different drones and different agents and continue the mission afterwards. So try to do it a bit more efficiently. So last up, I'm just going to do a quick bit of commercial stuff here. We're actually going to do a theme day, as we call it, over at the ASTA facility on the 24th of November. We're going to do a physical demo of this, so we actually believe that it is mature enough now to actually try and have some hardware out there and flying and driving around. And we're of course also going to do a virtual demo, and there's going to be some talks and discussions. So, if any of you are interested, please let me know, and I'll send out an invite to you. Thank you for your time.
Thank you very much, Morten. If there are any questions?
They're looking forward to the coffee break.
Yes, of course, but we have time. In the development of this protocol, what has been, you have put a lot of emphasis in the utilization of this peer-to-peer protocol. Have you, so to say, assessed other alternatives, or what have you driven you ultimately to choose this, so to say, specific type of communication protocol?
Well, it was kind of the purview of the project to use peer-to-peer algorithms, but we decided on that after looking around, seeing what was out there. And basically, when you talk about network communications, you have two ways of doing it. You have peer-to-peer and you have client-server. And as we want to do here, we have agents flying around, and they are peers inherently. So we wanted them to communicate directly, hence the choice of peer-to-peer, sorry. And that was the reason why. We also looked into, and I mentioned that some of the work done on peer-to-peer terminology has actually been done over many years on a fairly heavily stress load. And we thought that would be a great inspiration to work on that, because if you can withstand the combined might of the EU and the US and still continue your network, you got something going on there. You just have to realize that.
I have another question concerning the aspect of, let's say, safety, security, fault tolerance. Features, so to say, to detect malicious intrusions are already built in, is something that will be added at some point? How do you see this challenge?
So to detect adversaries?
To handle malicious intrusions, not necessarily an extra drone, which of course is not a part of the formation, so we know, but so to say, somebody trying to, for example, take down the network.
Sorry. So if we start with the first point, if we want to detect an adversary, it could be a person, it could be a drone or whatever, that's not built into the system as say, but you can add it in the configuration file that this is a point of interest that you want to handle. So it's just part of it. But of course it's not core part of it, because that's a communication protocol, which is something else. If you go over to looking at attack on the network, well, you can always bring down a network. Like, we can't do anything. If people are badly enough wanted to take us down, they'll take us down. But again, by utilizing peer-to-peer and utilizing this hops over peers, it's also a bit more resilient than using classical client-server terminology. If you're using client-server, if I take down the server, the system is gone. Can't do anything about it. By utilizing peer-to-peer, and they can skip around inside the network, they'll just route around the error issue like the TCP/IP protocol does in its basics, and just mitigate the error. So we can never make it 100% safe. I think we can all agree on that, but I think it tops a level on compared to some other systems.